Yeah. Yeah, at the same time.
Okay. So let's kind of go over what we did last time. The exam went well. I don't remember the averages or anything like that because I was just graded like mad to get things done. Most of the mistakes would be just be a little more careful when you do things. There's a lot of just kind of like dumb little things like I'm pretty convinced people know certain things and just being a little on the sloppy side. I'm really fussy with details. And so I want you to be fussy with details. Okay. So with that said, let's kind of go.
One clarification. You said you were grading them, not the ferry?
I left them there for that damn ferry.
Okay.
And never showed up. You know, I left no instructions, even a beer, and that grading ferry never showed up. You know, damn ferry.
Did you leave beer for the ferry?
Yes, and it still did not show up.
I just want to know what the
And Lorna Dunes. Is there anything better than beer and Lorna Dunes? I think not. But no, even chicken wings. Yes. Okay, okay, so let's do look at what we have. We have our hash. And what is that hessian? It's an n by n matrix, and in our case, it's going to become ultimately a 3n by 3n dimensional matrix. Right now, we just set up kind of a 3 by 3, but ultimately, it's going to become a 3n by 3n dimensional matrix of all the second derivatives, including the mixed derivatives. And so the diagonal terms are nice. What were they?
Just the second derivatives with respect to one.
Yeah, just the standard ones. So we like this. I'll just put in 3 dimensions here. Like that. And then I won't put them all in. But let's put in this row here. What would that row then be? Yeah, so mixed derivative, then with respect to y, and then also with respect to z. So we have this fellow. We have this fellow. And this fellow ends up becoming this one. I'll stop it with this, and then you have all the others. And what did we say about this term and this term? They're the same, meaning that when you have a mixed derivative, and this variable is an independent variable, then the order doesn't matter. Okay, the derivatives here. So this matrix, we gave this another name. We said if we took the transpose of this matrix, what does it equal then? H itself. And if you take the transpose of a matrix and it equals itself, we call that matrix symmetric. Again, this is not important for the class, but since it was brought up last time, you go to quantum mechanics, and then you have to worry about the transpose followed by the complex conjugate, the transpose followed by the conjugate conjugate, followed by the complex conjugate. That combination is called a dagger. And then it's Hermitian matrix, then means that the dagger of a matrix equals the original matrix. Okay. That'd be a Hermitian.
Which means the eigenvalues are real.
The eigenvalues are real. The eigenvectors are orthogonal. Okay. And then as likewise, then they form a basis.
Yeah.
Definitely. Yes.
So yesterday you had like a inverse.
We're going to do that in a second. We're going to do the inverse now. So we looked at the eigenvalues of this, and what were the eigenvalues of this H? We said this is acting on something without an eigenvector here. And if it's truly an eigenvector of H, you get the vector back times a constant, and you call that constant the eigenvalue. And it's traditional to call it lambda, although you don't have to. And are there a whole bunch of different eigenvalues and eigenvectors? Yes, so we often put a little subscript line. So this would be the ith eigenvector, okay, and this would be the eigenvalue connected, or the ith eigenvalue connected with the ith eigenvector. Okay. And then we have the functions form. That makes sense? Then we did something with this. we actually formed a matrix that we called O inverse. And how did we define this O inverse to be?
Just
Sounds like the beginning of a song, doesn't it? O inverse.
column vectors, column eigenvectors.
Yeah, it's gonna be made up of the column vectors of the eigenvectors here. So this right here, so in the first column, I put the first eigenvector. Second column, I put the third. We're gonna call the second, and then the third. And again, if I had a three-dimensional vector here, a 3n by 3n dimensional vector, then I would have matrix. Then I'd have all the 3n dimensional eigenvectors in there.
Are there always the enough eigenvectors as we have to?
Yep.
Okay.
And then we said we could take the transpose of this fellow here. And if we took the transpose of this, it looks just like this, but
Transposed.
yeah, the eigenvectors are now going to become row vectors. And so this becomes V1 this way, V2 this way, and then V3 this way as well. But we also found out something about these eigenvectors. We proved that if you have a symmetric matrix, let me get this thing and I'll answer your question. If you have a symmetric matrix, what did these V's end up becoming? Orthogonal. So since H is symmetric, the eigenvectors are orthogonal. What does it mean to have orthogonal eigenvectors?
Product of two different vectors.
Yeah, I should take this one transpose times
VJ.
Vj, and if I does not equal j, then this is 0. Now what I can do is I can actually, when I equals j, and this equals a constant, I can divide through by that corresponding constant squared, and we're going to do that today, and I can actually make this to be 1. So if I equals j, we normalize vi such that I get vi transpose vi equals 1. So give me then a fancy schmancy way of writing this. The fancy schmancy way of writing this is vi transpose vj equals now
Delta IJ.
or Kronecker delta ij. What does that Kronecker delta do? It takes on two values. What are they? 1 or 0. When is it 1? When I equals j. When is it 0? When I does not equal j. Now, why was this useful? Because if I take my little the transpose of this O inverse, if I multiply it by my O inverse, what did that give us?
Identity.
That gives you identity.
That's all. Just a quick notice
Yep.
on this question. Just to keep
I have this over here. Let me. Now I feel complete. Yes.
just to keep you consistent, like you forgot the transposes on the vectors, like
I
they
should
look
put
like
the transpose here, but I applied it by this
Yeah,
right
they
here.
look-
I like this. Like this. But if you want, I can.
we wrote it with transpose.
Is that how we wrote it last time? Okay, it should be consistent. Yep. So what we said. Is that if I do this fellow here, transpose this times this guy here, this is equal to 1 0 0 0 1 0 0 0 1. So this right here, this is the inverse matrix of O. So this right here, this is actually our matrix here. And so what this means here is an orthogonal matrix means, and then I should say this O, this O is called orthogonal. So O is called an orthogonal matrix. Okay, and then an orthogonal matrix means that the transpose is equal to the inverse. O is orthogonal. And all transpose equals. That's the formal definition, what it means to be reflective. And what does it become in quantum mechanics?
Unit.
Yeah, it becomes unitary because you have to take the dagger. So what happens when you do quantum mechanics, if you take the dagger of a matrix is equal to its inverse, then you have a unitary matrix. Which means it doesn't believe in the Trinity, and so if they were condemned, then basically they also see it. 25 AD. Okay, so let's go on with this. Okay, questions for that?
Maybe it's Muslim.
Okay.
Either Muslim or
They could be. Yes.
So yeah, like what is like the like negative one, like what is an inverse matrix?
An inverse of a matrix is by definition anything if you multiply by it, the original matrix, you get one. So. Okay, so an inverse of a matrix denoted by basically -1 means I'll say like A inverse means that A inverse times A equals A times A inverse always equals the identity matrix. That's what it means to be an inverse. So you take the matrix here, whatever it is, and it doesn't matter which side you multiply the inverse by, you always get the identity matrix.
they're inverses of each other.
Well,
They're inverses of each other, so
Yeah.
it doesn't matter.
so this right here, the identity matrix here, this is an n by n identity matrix. And I'll denote that with basically, this is kind of a fancy one, okay? I'll put 2 lines in there because it's n by n. So this is just n by n ones all down the diagonal. Okay. That makes sense? Now, we want to get to the point of, I want to convince you of what can you do with all this? So we showed the last one. Showed that you get this O, and then remember how we actually wrote this last time I wrote it, it's that, we wrote it like that. Times this H here. Times O inverse. What did that end up equaling?
Yeah, diagonal.
All the eigenvalues of H. This ended up here equaling all the eigenvalues, 0, 0, 0, 0, 92, 0, 0, 0. If this were a 3n by 3n matrix, then basically this would then be a 3n matrix. All the eigenvalues would be down the diagonal. So this right here is called a diagonal. This I'll define this to be H prime. H prime is just the diagonal. Very good. Of H. With all of the eigenvalues. All the eigenvalues of H along the diagonal. Okay. So let me show you how this goes, and then we can actually now then formally define a max, a min, and a transition point. Then I want to do an example of how this actually works. And since I'm just getting to this point, and homework 3 actually involved actually calculating one of these things, obviously I have to take homework 3, actually make it due yesterday. No, it's actually gonna be due after break. So what can we do here? So here's our original. Here's our original problem. Okay. I'm gonna multiply everything through by O. This is a number, so I can just put my O here. Okay, now we get to use our one of our 4 important math techniques. Let's review our 4 most important math techniques. Add 0 in a clever fashion. Multiply by 1 in a clever fashion. Separation of variables. Taylor expansion. Okay. Which one? Taylor expansion. No. Which one? Multiply by 1 in a clever fashion. And I'm going to put multiply by 1 in a clever fashion right there. I'll put it. 1 right here. I solved it. Give me a clever way to write 1. The identity matrix. Hey, give me a clever way to write the identity matrix.
O inverse times O.
O inverse times O. This whole thing here is just 1. N by N matrix 1. Well, I'm going to call this right here O acting on VI. I'm going to make that a new V matrix. I'm going to call this V prime. Hey, well, this is lambda I. This is V.
Can we figure out what that is exactly?
Turns out we can. Okay. Hey, well, but what is my buddy here? That's my H prime, which is purely diagonal. Like this. So what I end up with is exactly the same. I've basically gone to new coordinates. So this right here, this is going to be some new coordinate. And in this new coordinate, this right here is diagonal. Okay. That's kind of neat. So what would this mean here? So this right here, this is this right there. This is just the H matrix, the original H matrix, in some new coordinate system where the new eigenvalues, just the vectors, are denoted by VI prime. So now let's figure out what this means. So if I have something like this, so here's an example.
What is O code in this case?
What?
Like, what is O code? Like, what are these
It's
matrices?
just an orthogonal matrix.
Transformation matrix from one coordinate to another.
That'd just be an orthogonal matrix and it corresponds to a rotation. Okay.
Rotation.
You didn't have classical
Yes.
mechanics, but it turns out that when you have an orthogonal matrix, but you did have GR.
Yeah.
An orthogonal matrix is just actually going to be kind of a generalization of rotation. That made no sense. Don't worry about it. So let's say, give you an example here. If I have this, okay, what does that mean here? That means if I look in this new direction, whatever this new direction is in this case here, I'm seeing a positive second derivative. So let's say here's my new coordinate system, whatever this is. So here's my new x axis, whatever that is. So if I look in this direction here, I'm getting a positive second derivative. What does that mean? How would it look? What does the second derivative refer to again?
Concavity.
The concavity, that curvature there. If that's positive, what does it mean?
It's concave up.
It means it's a maximum. Okay, but now if I look in, I mean, it means it's a minimum because it's like this. Okay, if I look in this direction here, what am I seeing?
Positive change.
I'm seeing a positive vector here like that. So what does that mean? I mean, a positive eigenvalue.
It's a minimum.
Still minimum in that direction. Okay.
It's
Now, if I look in the last direction here in this direction, what do I see?
again, minimum.
I'm seeing a minimum. So it doesn't matter what direction in these new coordinates. It doesn't matter what direction I'm looking in. I'm seeing nothing but a minimum. So that point will be a true minimum. So when all these eigenvalues are positive, you have a true minimum. And that's going to correspond to, for an energy landscape, in turn, that'll correspond to a inherent structure. Okay? So what that means here is that since second derivative positive in each of these new directions, we have a true minimum. Now, let's say instead I had this. Let's say now I have that. So here's my new axes here like that. Now, if I look in this direction here, I'm getting a negative second derivative. What does that correspond to?
Maximum.
A maximum in that direction. And then if I look in the next one, a maximum. Look in the other direction, a maximum. In that case, in these new coordinate systems, any direction I look, I have a maximum. What does that mean then? I have a true maximum of the function. So this will be, since second derivatives are all negative. In each of the new directions. We have a true maximum. Yes.
So for a system, it would be a 3M by 3M page.
Correct. Yep.
Okay. So what are the eigenvectors and eigenvalues of the Hessian represent?
They're going to be basically, it's a generalization for three dimension. Second derivative.
Argumentos directions.
Yeah, but eigenvectors, what is that?
They're going to be basically, it's going to be they're going to be the new coordinates. Okay, that you're going to make. And so it's not going to correspond to one particle. You can't have necessarily this coordinates of one particle. It's going to be some corporate.
Yeah.
Good luck. Okay, now let's do the interesting case of positive negative. Yes. Let's say I have 2, 1, minus 3. Let's figure out what that was. So, I'm looking in this direction. What do I have? I have a minimum. That looks good. Okay, so in this direction, I'm getting a minimum. This direction, getting another minimum. This direction, a maximum. Okay. In 3 dimensions, this is almost impossible to see, but 2 dimensions, we can understand it. It's really a horse's cell. Okay. So in 2 dimensions, in a 2D problem, we might have let me just give you the 2D version. I might have 1, 0, 0, minus 2. So that means in this direction here, I have a, so imagine here's a horse's saddle, right? A horse's saddle looks like this part. So in this direction of the horse's saddle looks like that. But what happens if you look at the other direction of a horse's saddle? It's like this. Okay. So you're getting this type of behavior in one direction, and this behavior in the other direction.
It's a Pringles chip.
Okay. Same thing. Okay. They're made from horses.
Okay.
That's it. What happens when a horse dies? They become a Pringles potato chip and glue. Okay, so that's what happens. It's a very versatile.
Singeing twist too.
Exactly. But that's how they make it. So the glue that isn't used is used to make Pringles potato chips, or vice versa. We're learning a lot. So this is actually going to be kind of the three-dimensional version of this, which you can't really easily use because it's going to be a minimum, then maximum. 3 dimensions. What does that mean? I don't know of any shape that's easily.
It's in 4 dimensions technically, right? So like.
Well, this right here, you'd have X, Y, Z like this.
in the
And so
back-
the actual function itself would then have a 4th dimension like
Yes.
that. And how you actually represent that is, good luck with that. What? Wow.
That's what I was.
Yeah.
So if we're trying to figure out how likely is the transition over this minimum.
Yep.
Would that depend on how many of the points are maximum?
Yes, it can. So we give this a name here. So when you have one minimum here, you call this, okay, so this becomes a transition point. Okay, so this is a transition point. And the fact that there's only one of these means it's at a first order transition. So when the eigenvalues are positive and negative, you have a transition point. And so what happens here is that if there's only one negative, you have a first order transition point, 2 negatives, second order transition point, so on and so forth.
And that is not related at all to phase transitions.
Yeah, but you can have up to 3n order, transition point or 3n minus 1.
Well, you have to have positive and negative, so no matter what, you can't have all 3. So, yeah.
But why wouldn't all 3 and why wouldn't an absolute maximum be a transition point? What's the problem with that?
Well, you could call it that, but no one calls it. They just call it maximum. So it's a term.
Okay.
So if there is only one negative eigenvalue, the transition point is called a first order transition. Two negative eigenvalues. Second order. I'll say transition. And so on and so forth. Okay. So now I want to, so that's the class. So now we've classified these things here now. And so all I want to do is show you how you actually go about calculating them. And then what we'll do after break is that once we know how to find inherent structures and transition points, we can actually then start making physics out of it. So what we're going to do is that to be at a certain minimum here, or inherent structure, there's going to be a certain probability to be there. And what we're going to find out is that we can have transition, we can have actually rate of change going from one inherent structure to another. Sometimes those transitions can be really fast, equilibrium. Sometimes they're going to be pretty slow. Then we're going to start leaving non-equilibrium. We're going to start living in equilibrium, having non-equilibrium systems. Sometimes it gets a little more complicated because maybe over here, I have really, really rapid transitions. So I have a local equilibrium here. Maybe I have fast transitions over here, so I have local equilibrium here. But maybe overall between the two things, it's a slow transition. So overall, it actually, the landscape's going to fracture. You're going to see that. And that's what's going to happen in the glass transition. So that landscape is going to fracture into a lot of little regions, local equilibrium. But overall, it's going to be a non-equilibrium transition connecting all. And that's what took John and I forever to figure out. Well, it's still like 4 or 5 years.
I'm so very considered very fast.
So, how do we find? eigenvalues of a matrix of a n by n matrix. We're proving we're talking about us and proving out to a five basis.
Okay, sure. But then if you have that, you can, multiply by the genome, okay.
Okay, so we're going to do the following. So we want to basically solve this. How do we solve? For the VIs and the lambda i's. Again, for those of you who will be taking quantum mechanics at some point, guess what? You're getting a big jump ahead because it turns out that you're going to do this all. And even for classical mechanics, if you remember, we did this when we did normal modes. And it comes up. And also you do when you, if you remember when you had the moment of inertia tensor, that we actually went to the frame principal axes where the moment of inertia tensor was actually diagonal. And so the eigenvectors became the axes of the principal axes and stuff like that. Okay, so use it a lot. That's the important thing. And we get to use one of our standard math tricks. Okay, hey, let's think about which standard math trick we're going to use.
Multiplication by one.
Multiply by one. And where will we put this crazy one? No, never bad guess. Okay, right here. There's my one. But if you remember, what is the rule for one? The one must be a clever one. So how can I write one in a clever fashion? As the identity matrix. So I can write this as lambda I. One. Right? Because anything, when the identity matrix multiplies anything, you always get the original thing back. Okay, so now what I can do is I can take this to the other side. By the property that I like to call subtraction. Okay. I know. I like to live on the edge. Okay. And what I can do is I can then pull out a VI here. And now we have to do a little review. Well, right here. So recall 2 points from linear algebra. Here's the first point. I think we only need 2 points. If I have something like this, if I have A times X equals some constant here, this is a constant matrix. Constant column matrix. How do I solve for X symbolically?
Multiply by an inverse.
I multiply both sides by the inverse of A. So I multiply both sides by the inverse of A. The inverse times A is, by definition, that's true. If it's a true inverse, it has to be the identity matrix. That will give me 1 action X. Then it's like here goes to X. My X values would be the inverse times C. We're going to come over here. Make this 3. Okay. 2. If C equals 0, we have A acting on X equals 0. So what would we normally do?
Multiply by the.
We multiply by the inverse. And if I take the inverse times 0, that's going to give me 0.
So that's the truth. So what X.
Yes, it is. So this gives me 1 times X equaling 0. In other words, X equals 0. Now that's true. I could put in X equals 0 and that equals 0. But a mathematician would call that a trivial solution. So this is called. Trivial. Okay. We don't want that to happen. So if that can't happen, what can exist? There cannot be
An inverse for the matrix.
an inverse for the matrix here. So for AX to have a non-trivial solution, the inverse of A must not exist. Sounds like we're making a metaphysical statement. It's denied existence. So its essence is that it doesn't exist. Which case, can we talk about its essence? I think not. Okay.
But if it has an instance, how can it not exist?
So what's the condition? I think we call this point 3. Okay. If the inverse A does not exist, then the determinant of A must be 0. And I think we need to prove that statement.
Think so?
Yes. True. Okay. I know that A inverse times A equals what? 1. 1. Now let's take the determinant of everything on both sides. What's the determinant of the one matrix?
1.
1. Now, there's a property of determinants. I think I said that right. There's a property of determinants that if I have a whole bunch of matrices being multiplied, if I take the determinant of the product, this is equal to
1 over the products of the determinant?
well, the determinant of the products of each of these. So this would be the determinant of A times the determinant of A inverse of the determinant of A.
In other words, like something like 1 over.
So this means that the determinant of A inverse is 1 over A. Remember, determinant is just a number. So this is a number. Okay, if this doesn't exist, there's only one way to make that not exist. That would be to have this be 0, because 1 over 0 is undefined.
Okay, first time I hear you speaking mathematics. Usually we say 1 over 0 is infinite or large. Your wife would be proud.
She may not like that proof. I showed her a proof of the direct delta function and said it does something, and she just turned to me and went, "You know that makes no sense."
Why?
Yeah, I like that. I made the mistake when I was newly married of telling Catherine that I understood limits as well as she did. Then she proceeded with multiple examples to show me that I had no clue what I was talking about. I think she made her point after the first example. That was just me. Okay, so,
You.
didn't happen again. Okay. I also made the mistake of telling her when I was newly married and foolish that my mother baked a better apple pie than she did. Ooh, no, never, don't. For those of you who get married, do not, under any circumstances, let any variation on those words come out of your mouth. No.
Sounds like recipe for retarded.
No, it turns out she proved that point too. So, it just, no. We're just never gonna apple pie ever. No. Yeah. What are we doing? Okay, so we're going back to our problem here. So our problem is this.
You were forced to write the more space in the science.
Okay, this right here is what size matrix?
N by N.
This is an n by n matrix.
3 N by.
It'd be ultimately a 3n. Okay, so this is an n by n matrix at canvas here. And what do I want this to exist here?
You want this, its determinant to be 0.
Yeah, I don't want this to have an inverse, because if it has an inverse, I can multiply by the inverse on both sides, get my vi equals 0, which is a trivial solution.
I mean, it's okay if it does, but that's just like one set of solutions. We want us to find all of them. So another set is when it doesn't.
This is called the trivial solution for good reason. Okay. So we do not want this n by n matrix to have an inverse. We haven't used ergo in a while. Ergo. We want the determinant of h minus 1 lambda 0. Okay. There. That's how you do it. Let's do it now. Let's do an example here. Let's do an example. F equals minus x squared plus y squared plus 2xy. Just made this up. The question is, part A, find the extremum of this function. Part B, find whether determine whether that is max, min, or transition point. There'll be more parts, but I think this is all we can get to today. Okay, so let's figure out the extremum. So to figure out, meaning the extremum is going to be the point that you have either a max, min, or transition point. How do you go about finding that?
Y equals minus x.
Or do you take a derivative?
I mean, you can complete the square of it
This is
and take the derivative. Minus 2x plus
minus
plus
2x plus
2y.
y. Okay. And I want to set that to 0.
Mhm.
Okay. Because only on the middle. And then I do then the partial f with respect to y. Is 2y plus 2x. If I add these two equations together, okay, they cancel. This is being 4y equals 0, so y equals 0.
Mhm.
How do I find the next?
Plug it back in.
Yeah.
I take this and I put it back into either one, say here, and what does that give me?
X equals 0.
That thing gives me x equals 0. So the claim is the point 0, 0 is an extremum. The question is, what kind of extremum do we have? Dun, dun, dun. What do we have to look at?
Secondary.
The second root. Well, let's look at our buddy here. Minus 2. Okay, let's look at this one here. Hey, let's look at this one here. So if I were to construct my Hessian,
And that's bucks.
Yep.
We have to kind of. We have to do it at a point, right? So we're construct hashing this at a particular
no,
point,
this one's
easier because
we
It's
I
not-
wanted something I can do
these
quick.
do not come out as functions at
Correct,
points.
correct.
But like
We have
technically,
we have a point, which is that's what I didn't say.
okay,
Normally, you would actually have to evaluate it.
like these can be functions of coordinates.
Well, the points here, these would be real points.
Yes.
Okay, and then what you'd have to do is that
Plug in.
these can be, will depend on who knows what.
Mm.
They take corresponding points here and here, and you're getting numbers. Okay, so what does our little matrix here become? Minus 2, 2, 2. And so what we want to solve is this H VI equals lambda VI. What was our trick? We put in the identity matrix here. Take this to the other side. We write it like this. Do that, what do we get? We get minus 2, 2, 2, 2. Minus lambda I. Now, what is the identity matrix? 1, 0, 0, 1. All this. Axiom, what do you mean? Well, let's write this in a slightly more compact one. And so this is minus 2 minus lambda I. 2, 2. 2 minus lambda I. Okay, so for this to not exist, not to have an inverse, what has to be the case?
The determinant has to be 0.
The determinant of this has to be 0. Determinant of so if I take that and I'm going to rewrite this from here. I'm going to write this as minus 2. I'm not going to write it like that at all. I'm going to write it as minus 2 plus 1. So then if I do this, it's going to be this diagonal minus that diagonal. So this would become minus 2 plus lambda I. I'm this guy. 2 minus lambda I, then minus this guy here, minus 4. This is minus, if I multiply this out, I get 4 minus lambda I squared. Because the cross terms go out, minus 4 equals 0. So this gives me that lambda I squared, plus sign here, minus 8 equals 0. My lambda I is plus or minus square root of 8. Plus or minus 2 square root of 2. So what kind of point do I have? Do I have a max, min, or transition point?
Transition.
How come?
Different signs.
Because I have a plus or minus. So this point here, this is a plus or minus, this is a transition point. And we'll call it good for here, and then what we'll do, when we get back, we'll find the corresponding eigenvectors for this. And how do you find eigenvectors again? You take one of the eigenvalues, and put it back in the original equation here. I'm going to write the V as like an AB. I'm going to figure out what the A and B are. I'll have to do that for each of the eigenvalues. And then Shazam, we got ourselves some eigenvectors. Okay.
Just you plug them in right now.
I never like putting them in this one here, I just.
If like VI is AB, you
Yeah,
can
I mean,
multiply it out.
you can. Right. Yeah, so if you have a discriminant, if you have this, A, B, C, D, this only works for 2 by 2. This minus this.
I do want that.
Take your use of.
So happy. Rocky, return hit my